So, today we discuss on circle. So, different properties of circle. So, circle, okay. So, what is circle? We know circle is a curved line and there is a fixed point, it is called center, and this curved line is sometimes called circumference, but this is actually a circle. The point, the center is not the part of the circle, inside the circle. The other thing, chords and arc, the arc is part of the circle, but the chord diameter is not the part of the circle. So, what is the property? The definition is this. So, from the center, distance to the any point on the circumference or on the circle is equal. That is the one and only one property, and this defines circle, and from this property we will prove everything, right. So, what is the first thing? The first thing is this. So, if you have a chord, this is called chord, and if you join two points on the circle, the line segment is called chord, right. So, and this is the center, then if you draw the perpendicular to the chord AB, then it meets the chord at the midpoint, right, you know this. So, if ON is perpendicular to AB, then what happen? Then AN is equal to BN, right, and converse also true, you know that. This proof is easy, you just join OA and OB, and by some congruency, what congruency is, one side is common, other side also common, RHS, right, one RHS. So, and conversely, if AN is equal to BN, N is a point on AB such that N is a midpoint of AB, then ON is perpendicular to AB. How do you prove this? This is just by SSS, because AN equal to BN, OA equal to OB, and ON is common, so SSS. So, this is easy. Now, what are the other important properties? This. So, if you have any arc, and this is called the arc, any part of the circle is called arc. So, AB is an arc, is sometimes we write like this, so curved thing. So, AB is the arc and O is the point, then the angle AOB is called the angle subtended by the arc AB or the chord AB at the center. But there are other thing also. And if we take this thing, we join it to other points, say P on the circle, then this angle APB is called the angle subtended by the arc AB or chord AB at the circumference. And we know the which property is here true. This angle subtended at the center must be the twice of the angle at the circumference. So, angle AOB is twice angle APB. And how do you prove this? This proof is as actually two different figure is there. One figure is like that, actually three different figure, another figure is like this. Now, the P is like this thing, and another figure is like this. Okay, this AOP are collinear. Okay. Proof, the proof is almost same. Here AOP is collinear, special case. Almost same, we just join, say this is P, join PO and is just extend this sum, and then these two angles are equal. We know if two sides are equal because both are radius, right? OP and OB is radius, so this two angles OPB and OBP they are equal. Similarly, these two angles also equal, right? Now this angle is just twice of this. Say if you say AX, this is AX, this 2x. You know the exterior angle is sum of the two interior angles, opposite interior angle. Similarly, this is y, this is y, then this is 2. So this is twice x plus y, and that angle subtended at the circumference is x plus y twice. But here the proof is slightly different, you know that. If you add this, join this, similarly here AOP, here also AOP. Now the AOP, which angle? This angle. This is twice of this angle, right? And other triangle is similar. So BOP. So BOP. In this situation, this is x, y, the whole thing. So this is 2 into y, right? Now this triangle, and this 2, this is y, this is also y, so this is 2y. Now you have to take the difference. 2y minus 2x is equal to, here this is APB is y minus x, and AOB is just twice, yeah, y minus x. So, and this is much easier proof here. It's just a double. You know this, these two are equal. So this is twice. Since AOP is collinear, that is a twice of this. So it is just nothing add, nothing subtraction. You have to add in this situation, subtract, and here nothing. Okay. So this is the most important thing, and from this, what we can say, we can easily say that if we take two different angles subtended by the same arc or same chord, one say APB, where P is on the circumference, and another say AQB, Q is another point other than P, right, in circumference, on the circumference, then they must be equal, right. So these two are equal. Why? Because both are half of the angle subtended at the center on the same arc, right. So there are infinitely many angles subtended by the same arc to the circumference, but there is only one and only one angle at the center subtended by the same arc. So in the, for all angle subtended at the circumference is half of the fixed angle. Here obviously AB is fixed. If you change AB, then it is okay, change. Now okay, so next thing, next part is very interesting. Here the arc is same. Now if I take the arc length is same, but in the two different part, right. So this is a circle, and you take one arc here and another arc say here. Now say this is AB and CD. Now both the arc length is same. So AB, the arc length of AB is same as arc length of CD. And in this situation, what happens? This both angle are equal at the subtended at the center. Why?
Because the chord passing through those angles are equal. chord is connecting the points of AB and the CD. They are the same.
Why?
Because they are passing the same arc.
That we have to prove. If we arc length is same, then we have to prove the chord length is same. If the chord length is same, then the arc length is same. So three different things: the angle subtended at the center, arc length, and chord length. If one of them is equal, then other two must be equal. Why? Okay. And for this reason, to prove this, we have to use a very important result on circle. The result is, you know this, if O is the center and this angle is theta, then there is a very important thing. So, theta is nothing but the arc length of AB divided by the radius. This is the definition. Basically, this is the definition of the angle, right? Because arc length is AB divided by the radius OA or OB is the angle theta. That is why the whole length of the circumference is 2 pi r, because the total angle is 2 pi, so 2 pi r, right. So, this is very interesting and important. Actually, you can't prove this. This is actually an axiom. And using this axiom, we can easily say that if arc length is equal, now radius is equal by the definition. So, there is one definition and one axiom. In circle, there is actually two things important. One is this, all the radius are equal, and other is this angle theta defined like that. So, if the arc length is equal, whatever when where this is here or there, and the radius is equal for everything. So, O is actually CD. So, this actually implies AB arc length divided by OA is same as CD arc length divided by OC, because OC and OA are equal, both are radius. Now, by definition this is angle AOB, and by definition this is angle COD, right? It's clear. So, this is actually from definition and the axiom. Similarly, if the angle are equal, then the ratio is equal by definition, and the denominator is equal, that is why the numerator also equal. So, that means if arc length is equal, so that means the angle AOB is equal to angle COD. Both side implies, is called if and only if. This implies the arc length AB is equal to arc length CD, and if arc length CD is equal to arc length AB, then angle AOB is equal to angle COD, right. So, this is just not from the chord, because there is no direct relation from chord to arc, there is no direct relation. The direct relation is from arc length to the center, angle at the center. Now, we connect this with the chord length, right. For chord length also we know these are equal. So, now draw a different picture. Circle, and we take two different chord now of the same length AB, and in different part it is CD, right. So, now AB and CD is equal, is given. It is given that AB is equal to CD. Now, is this angle subtended at the center is equal? It is clear. Why? It is by congruency, right. It is no different, no definition is needed here. Definition is related to the arc length, but here it is just a triangle. So, these two are equal, and this equal to this, and this also equal to this. So, SSS congruency, the opposite to these two sides must be equal, this angle. So, this implies angle AOB is equal to angle COD. Similarly, conversely, if we take the angle AOB is equal to angle COD, then what happened? Then by side angle side. We do not know whether AB equal to CD or not. So, we can't use SSS. This is equal to this equal to this, and the in between two arm the angles also equal, it is given. So, that means it is congruent, these two triangles are congruent, the other side must be equal. So, side angle side. So, this actually both side implies, if both side implies they are equal. That means what? That means if angle are equal, then the chord are equal. If the chord are equal, then the angle means angle subtended at the center are equal, and if angle equal, then the arc length is equal, and arc length is equal, if angle are equal. That means that if angle is equal, then arc length are equal, chord also equal. If chord length is equal, then the angle is equal and arc length also equal, and if arc length is equal, then angle are equal and chord also equal. So, if one pair is equal, then the other also the angles and chords also equal. So, this is a important part. So, that means if the three thing AB, arc AB is equal to arc CD, or chord AB, that is the length, line segment, and this angle AOB, O is the center, angle COD. If 1 is true, then 2, 3 also true. If 2 is true, then 1, 3 also true. If 3 is true, then 1, 2 also true. That is important. Okay. Now we'll go into the more deeper part. Now we have a circle, and we took four different points, say A, B, say C, and say D. Four different points on the right. So if 4 different point or 3 different point or 5 different point or maybe more than 3 different point is on the same circle, then they are called concyclic, right. So A, B, C, D are concyclic, right. Now if we join AB, BC and CD and AD, we get a quadrilateral, and this quadrilateral is called cyclic quadrilateral. So, the same thing. So, ABCD cyclic quadrilateral is actually same as to say A, B, C, D, 4 different points are concyclic. So, actually the same thing. If I say A, B, C, D 4 points are concyclic, that is same as to say ABCD, the quadrilateral ABCD is cyclic. Now the question is, how do you know? If you first draw the circle, then take the points, then okay, they are concyclic. But if you do not know whether the circle on the circle or not, we first draw the quadrilateral, and then we ask whether it is on the this cyclic or not. Now the easy thing is, if I took one point, then we can always draw a circle, right. So if I have one point, take other point, join these two, take this as a radius, and this is other point like O, say O, and this is a center. So we draw a circle passing through that point A. Now if you have 2 points, how do you get a circle passing through these 2 points? Do you know? If you have 2 different points, can you draw a circle passing through these 2 points AB? How do you draw?
Drawing the center of the two lines and then
Center of the line, or say a midpoint.
midpoint. Yeah.
How do you get the midpoint?
Using
Perpendicular bisector. Is first join AB and draw the perpendicular bisector. Take the midpoint. Okay. Now you draw a circle using that midpoint as a radius. Now the interesting thing is, you can take other point also as a center. You can take this point also as a center. On the perpendicular bisector, any point on the perpendicular bisector is equidistant from A and B, right. Since it is a perpendicular bisector, this is a 90 degree, this is common side, this is a midpoint. So side angle side, so using side angle side, we have this AP equal to PB. So we can take P as center. So there are infinite many circles which passes through A and passes through the end point of the line segment A and B, not the straight line, whole straight line, the end point of the straight line of the line segment. Right. Now, if you have a one point, then there are infinitely many circles. You can take center as other than that point, any point. Now, if you have 3 points, how do you draw the circle passing through all? That is called circumcircle. That is a circumcircle passing through ABC, all 3 points. How do you find the circumcenter? Center of the circumcircle is called the circumcenter. Yeah, no, not the, you just take the perpendicular bisector here. 2:1 ratio is the centroid. Okay, perpendicular. If you take the median and 2:1 ratio, that is the centroid. Now take the perpendicular bisector, because you have to first draw a circle passing through AB. So take the perpendicular bisector of AB. You need that center also passing the circle passing through AC. So take the perpendicular bisector of AC. So any point on the perpendicular bisector of AB, if you take the center, the point center as a point on any point on the perpendicular bisector of AB as a center, then that circle passing through AB. And if you take any point on the perpendicular bisector of AC as a center, then that circle passing through with the radius, obviously radius OA. So that passing through OC, A and C. Now if you want all, no need of BC. If you want the circle passing through AB and AC, all 3 points, A, B and C, then we need the intersection of the perpendicular bisector of AB and perpendicular bisector of AC. So perpendicular bisector of AB and perpendicular bisector of AC say meet at some point O, that O from OA is equal to OB. Similarly OA equal to OC. So no need of take the perpendicular bisector of BC, and actually you know the all 3 perpendicular bisector is concurrent, right. So passing through that circumcenter. So we get a exactly one circle, but there is a small problem. If ABC are collinear, then we can't draw a circle, because if ABC is collinear, the perpendicular bisector of AB and BC is they are parallel, that is intersect, no centers. And actually there is, we can't have 3 point, we can't have 3 point on the circle which are collinear, right. The 3 point on the circle and they are collinear, it cannot be true, impossible, because from the center 3 points have the on a straight line 3 point have the same distance, it can't happen, right. Say if you have a line say A and 3 points on that A, B, C, and there is a point O, OA is same as OB, it can't be true. It can't be true that OA is equal to OB is equal to OC, can't be true. Yeah, why it can't be true? Say ABC is collinear and it can't be true OA is same as OB is same as OC, because it is just easy, you know that in a triangle the bigger opposite side to the bigger angle is bigger. Now if say these two are equal, then these two are equal, but in this situation this must be smaller than this, that means this must be smaller than this, that means this side is smaller and this is bigger, right. If I say these two angles are equal, in that situation this angle is larger than this, so this side is larger than this, so it can't be 3 sides are equal, 3 line segments are equal. Now if one point is given or 2 point is given, infinitely many circle. If 3 point are given, then maybe 0 circle, no circle, if they are collinear. If they are non-collinear, exactly one circle. Now the question is, if there are 4 different points, they may not be in the same circle. If they are in the on the same circle, we call it is concyclic, right? May not be on the circle. Why? Okay, it is very easy. You take, you draw a circle, take 3 different points A, B, C here, and take the other point very far from there, D. So you can't draw a circle passing through all, not only D, no, just not D, A, B, C, D, all. You can't draw, right? If there are 5 points or 6 points or more than 3 points, maybe no circle passing through all points, or maybe actually if it has a point, a circle is passing through, if there exists a circle passing through all points, that circle must be unique. There is one and only one circle, more than 3 points, actually more greater than or equal to 3 points, 3 or more, right? And in the situation that all points are called concyclic. If there are say 100 points on the same circle, one circle is passing through all 100 points, then we call the 100 points as the 100 points are concyclic, right? Okay. So this is called cyclic quadrilateral. Now, how do you know this is cyclic quadrilateral? That there are different proper proof there in books. I'll show the, yeah, right, but join this, obvious center is the important part of the circle. Join all 4 points with center, and if this is x, then this is also x, isosceles, right? And this is y, then this is y, this is z, this is z, and this is w, and this is w. Then what happens? If we add all 8 angles, 2 into x plus y plus z plus w is 360 degree. We know the sum of all 4 angles of quadrilateral is 360 degree. So that means x plus y plus z plus w is 180. So x plus y plus z plus w. So sum of the opposite angle is 180 degree, right? So this plus this is 180. Similarly, okay. And what about the converse? If I know sum of the opposite angle is 180 degree, is it concyclic? How do you prove? Here we assume they are concyclic, and in that situation the sum of the opposite angle is.
4 points are lining on the circle and all the angles are.
Now we don't know whether circle is there, so now the problem is different. Oh, sorry, we don't know there is a circle or not. So the quadrilateral ABCD is given, and it is given that the sum of these 2 angles is 180 degree. Okay, if sum of these 2 angle is 180 degree, automatically sum of the angle B and angle D is 180 degree. So it is given that D, it is given to us B plus DCB is 180 degree. Okay. Now we have to prove that ABCD is concyclic, or that ABCD quadrilateral is cyclic quadrilateral. How do you prove that? Now we can't take the center now because we don't know whether it is on the circle or not. So basic idea is this, okay, you draw a circle passing through ABC. Obviously this ABC is not not collinear because it is a quadrilateral. Since it is a quadrilateral, 3 point is not collinear, any 3 point. So draw a circle passing through ABC. We can always draw a circle passing through ABC. So draw a circle passing through ABC. Now we have three different situations. D can passing through this circle, then done. Now if D is inside the circle, three different cases, then what happens? Okay. Now we draw a circle passing through ABC and D is point inside the circle. Is this true sum is 180 or bigger or lesser?
It's not possible of this particular case.
Now okay, now the question is if this and we have a we take a point inside the circle, say now we take this which point AB, say AB and this point is D. Okay, not AB, it is AC, sorry, it is AC, right? It's just AC 2 points and this okay, AC ADC. Now is this angle is same as the angle subtended at the circumference?
No.
Subtended by that arc is not, right? Is it bigger or lesser?
Lesser.
Oh, it should be bigger because if say D is the point on the center is double, right? If D is the point, D is the same as the center, then it is double of the, so it must be bigger, not smaller. So how do you prove? The proof is very easy. We just extend this, say up to E and join E and C. Now this angle ADC is equal to angle AEC plus angle DCE, that must be greater than AEC, right?
Yes.
It's very easy. Now the other way, if the ADC, say this point is E, same thing, we join this and in that situation AEC actually sum of ADC and ECD. Now it is bigger than ADC. So here the ADC is smaller than the angle subtended at the circumference, here angle ADC is bigger than the, right? Now we come here. Now same thing, we just take a point, we extend this, take a point where the extend AD up to the circle. Now say E is the point on the circle such that ADE is collinear. Now join this. Now clearly we already proved, what do we prove? That angle ABC plus angle AEC now. Now AB, C and E are concyclic. So this is 180 degree, that we know from the previous theorem. Now ADC is bigger than that, bigger than AEC. That means angle ABC plus angle ADC must be greater than, strictly greater than 180 degree. That means angle A plus angle C is less than 180 degree. Similarly, if D is outside the circle, then angle ABC plus angle ACD is less than 180 degree. In that situation, angle A plus angle C is greater than 180 degree. So three different situations, right? If D is outside the circle, then that D angle plus B angle is greater than less than 180 degree. If D is inside the circle, then D angle plus a B angle is less than 180 degree and D is on the circle, then is just equal to 180 degree. So, 3 different situations, that means it is if and only both side implies. So, that means what we prove, that A, B, C, D are concyclic, what do you write this? Concyclic if and only if what? The angle A plus angle C is 180 degree, right? Both sides imply. Now, this part, angle A plus angle C is 180 degree, we write this result or this statement in a different way. What? So, angle A plus angle B is 180 degree, and if I say angle, sorry, not A, it is C, not B. Angle C. Now, angle A plus angle C is equal to angle B plus angle D. If I say angle A plus angle C is 180 degree, is it same as to say angle A plus angle C is equal to angle B plus angle C? Yes, because sum of fourth angle is 360 degree. If sum of four angle is 360 degree, right? Since sum of four angles 360 degree is two of them sum is 180 degree, then other two must be 180 degree, right? That means they are equal. So, if A plus C is 180 degree, automatically B plus D is 180 degree, that means they are equal. On the other hand, conversely, if we have that angle A plus angle C is same as angle B plus angle D, and we know sum of all four is 360 degree, that means the sum of these two is 180, the sum of these two 180. So, actually these two statement, this 1 and 2 are equivalent. We say ABCD is concyclic if sum of the opposite angle is 180, right? We can say in different way, ABCD is concyclic if sum of the opposite angles are equal, opposite pairs, two different pairs, sum of two different pair is equal, that we can say. Okay, clear? Why say like that, we will see in the next discussion. So, now the next thing. Now, okay, if this is called concyclic, then this quadrilateral is called the cyclic quadrilateral, and in that situation the circle is called circumcircle, right? The circle is called circumcircle. Now, the other way, now the circle is inside the quadrilateral. Now, ABCD is a quadrilateral and circle inside that. In that situation, we call it in circle, right? The circle is in circle, and this quadrilateral is called the circumscribe the circle. The quadrilateral circumscribe the circle, and circle is inside inside the circle or inscribed in circle. Okay, and in the previous situation, the circle is called the circumcircle, and the quadrilateral is called inscribed the inside the circle. Okay. Now, what is the property of here? No, you know, in the when a circle, we can draw a circle. Again, if you have three different point, not collinear, we can always draw in circle, right? You know that it's called the incircle of the what? Incircle of the triangle, right? Now say we have three different points and we draw the in circle, say smaller circle in circle. Now say A, B, C. Now if I take the other point D is here, can I draw a in circle? Maybe I do not know whether it is true or not. So depends on the site, right? So, but always we can I okay, say we take a line like that, says this one and then say this is smaller one and now this is very big. Can I draw in circle? No. What? Sir? dA would be equal to DC? dA? dA would be equal to DC? No. No. May or may not be true. Okay. So it is true that if we take 4 different points, may or may not be there is an in circle, right? So what is the property? What is the result? I will prove that dA may not be equal to dB or whatever. That this thing is AB plus CD is equal to BC plus DA. This is the necessary and sufficient condition, right? So if the sum of the opposite sides are equal to the other sum of the other two opposite sides, then we can draw a in circle. That is why I write that previous thing this way. If the opposite angles, sum of the opposite angles are equal, then this is a we can always circumscribe a circle, and if sum of the two opposite sides are equal, then you can draw a in circle. Okay, now I will prove that. Okay, one proof is easy. If I assume that we have a circle inside the quadrilateral, this proof is easy, and the converse is slightly tough. So now question, what do you mean by in circle? What? Circumcircle means it is passed through all vertex. What do you mean by in circle? What is the property of the in circle? What is the definition of the in circle actually? Actually these sides touch the circle. That means the sides are tangent to the circle. So that's for to prove this we need some properties on the tangent now. Now this is a circle and we have two different tangent from outside point, two different tangent. Say from P it is A, this point is A, and the A and B is called point of contact, right? You know this is called point of contact. Point of contact. So point of contact. Then A point of contact is A and B. And P is a tangent, PA is tangent, where point of contact is A, PB another tangent, where point of contact is, and P is outside this. From inside you can't draw its tangent. Now we know that in that situation PA equal to P. How do you prove that? Joint center, say O is the center. No, is okay. And then we have two different triangle APO and BPO, and they are congruent, right? Why they are congruent? This equal to this always by definition of circle. What do they say? Sir, would there be a condition where we can draw both circle outside? Yes, I will discuss on that. Someone asks that is there a condition, what is the necessary and sufficient, very good question, what is the necessary and sufficient condition that we draw a circle inside the quadrilateral as well as the outside the quadrilateral. What is the condition for it? Obviously, if the quadrilateral is a square, we can always do this, right? But if it is a rectangle, it's not possible. Outside is possible, inside is not possible, right? For the rectangle, clearly for the rectangle, which is not square, obviously the rectangle which is not square, we can't draw in circle. But if it is square, we can draw in circle. In rectangle, if it is rectangle, we can draw the circumcircle, but not the in circle. If it is square, is not square. If it is square, then we can always draw. So now next theorem we discuss what is the necessary and sufficient condition for that, such that both circle we can draw the both circle. Okay, first we discuss this. So we have to prove that the sum of AB plus CD is BC plus ADA. Now why these are these two are congruent? OA equal to this is common. So one more thing we need, obviously we need to prove AB equal to AP, so we can't take that as a we need one angle. We know these two angles are 90 degree, right? Perpendicular RHS. So why this perpendicular? Why this? Again one theorem. If we have this thing, say POB, then if BP is tangent to the circle, then O is the center, then OPB is 90 degree. Why? Why? Tangent means the only one point touch the circle. So this the whole tangent exactly one point touch, that means no point inside that, right? This can't be a tangent, and this can be a tangent. So since this can't be a tangent, that means the B is the only point which is common to the circle and the all other point outside the circle, right? No point inside the circle. If some point inside the circle, one more point will be there on the circle. So no point inside the circle, all point outside. That means if you take any other point that is bigger than O, if you take any other point C, then OC is bigger than OB. Is by definition of circle, it's outside, and we know the minimum distance is the perpendicular. Why? Why the minimum distance perpendicular? For a line, say O is the point outside that, the minimum distance is the perpendicular. Why? Why the minimum distance? Is from the Pythagoras theorem. Pythagoras theorem. So it is a minimum distance, or you can do prove by the triangle thing. So this is bigger. Any point, if you take any point outside other than N on the line, then ON is bigger than OM is bigger than ON. That means this angle is bigger than opposite angle, right? Which is the opposite angle? This angle. So ONM is bigger than any other angle OMN. That means 90 degree. Why? It can be 120 degree, maybe. Now take another point this side. Take another one this side. So this angle also again, now this angle is also again bigger than any other angle here, right? That means what? That means both angles must be 90 degree, because if one of them is obtuse, other must be acute. And in that situation, if one is acute angle, say one of them is acute angle, so ONM is acute angle, then drop the perpendicular from O to that line, and that angle will be bigger than that acute angle, right? That means that triangle must be that angle must be right angle. This is one proof. Other proof is using just Pythagoras theorem. Using Pythagoras theorem, you can easily say, because in Pythagoras theorem ON square plus OM square is OM square. OM square plus MN square is OM square. So OM square is always bigger than the ON square. This is a proof using Pythagoras theorem, and you may not use the Pythagoras theorem. You can just use the bigger opposite to the opposite angle to the bigger side is bigger, like that, or opposite side of the bigger angle is bigger and opposite angle to the bigger side is bigger. Okay. So these two are congruent, that means PA is equal to PB. Now come here. So take this point like P, this point of contact P, Q, say R, this point of contact, another point of contact S. So what we get from here? So take same like say we just take the same thing like X, Y, Z, W. Here also. Now here also X, AS is X, so AP is X. Y, same type of proof. In that situation, the angle now here is a side. Z, CQZ, CRZ, W's, DRW, DSW, right? So clear. X plus W here is equal to Y plus, right? Sorry, now this X plus W plus Y plus Z. So AB plus CD is, what is AB plus CD? AB plus CD is X plus W plus Y plus Z. What about AB? Oh, and here is no, it is AB plus, not AB plus, it is so AB plus CD. So it is X plus, oh sorry, this is AB, X plus Y plus Z plus W, and other is AD plus BC. So it is X plus W plus Z plus Y. So this story clear. So that means if the opposite angles, sum of the opposite angles are equal for two pairs, then it is, we can draw not in circle, circumcircle, and if the sum of the opposite sides are equal to two pairs, then we can draw in circle. Now no, we already proved that if there is a, we can draw inside circle inside, then sum of the opposite sides are equal. Now we have to prove the converse. If sum of the opposite sides are equal, then we can draw a circle. Okay, inscribe this, right, inscribe in the quadrilateral, not the square. Now how do you prove this? Same idea like this, same idea like this. If D is on the circle, D is inside the circle, and D is outside the circle. Same thing we will do for here also. We draw first what? We draw in circle of just touching what? Touching, not, no, we can't, may or may not, we have to prove that. Touching three lines. But how do you prove that we can draw a thing touching three lines? How do you draw a in circle for a triangle? For triangle, how do you draw in circle? In that for circumcircle we need the perpendicular bisector. For incircle we need angle bisector, right? We need angle bisector. So draw angle bisector, and any point from angle bisector the distance is equal. Okay, and we do another angle bisector here. So this is I, and we know that from angle any point on the angle bisector, if of the perpendicular and of the perpendicular, these two are equal. then these two are equal. IF and ID are equal. How do you prove that? You see, two angles are equal, both are 90°, one angle side angle congruent. So that means IF equal to ID. Similarly, this since these two angles are equal, if we take the perpendicular from there to E, then IE is same as IF. So all are equal, and now take I as a center and ID as a radius, then touch all three sides. So same thing. What will do?
Angle bisector from
So angle bisector from say A.
A, B.
No, not here. You if you draw two angle bisector, the third also passing through this, because already we have these two are 90°. So if you join this, now already these two are 90°, and these are congruent. This is common, and these two are equal. So RHS. That means is 90 angle bisector. Now, if you do angle bisector of this and A and angle bisector of B, say they meet at I. Now what we can say? We can say that if we drop the perpendicular and perpendicular here, they are equal. Say R, this is AS, then IR equal to IS. Same logic. Same logic. Because this angle SAI is same as RAI, angle bisector. So this is 90°, so angle side. Similarly, if we draw perpendicular here, say P, then since RBI is equal to PBI, IR is same as IP, right? Now I don't know if I draw the angle bisector from C, whether it is passing through I or not. If it is passing through I, then done. Then done. Then the already three perpendicular drawn and they are equal length. The last thing is we have to draw a perpendicular on DC from I, and we have to prove that length of the perpendicular is same as the other three. But I don't know whether it is passing through that angle bisector passing through I, and that this is not true for all case, and that should be true for when this AB plus CD is equal to BC plus AD. Only that situation, what?
The perpendicular.
Perpendicular, all perpendiculars are equal. That means that third one is also, third and fourth both are passing through I. So that we have to prove. That prove the converse. Okay. So how do you prove this? Okay, draw the perpendicular, right? Draw the perpendicular. Draw the perpendicular. We don't know whether IQ is same as IP, or we already know that IS is same as IR is same as IP. But we don't know whether IQ is same as those, same as the other three. But what we know? We know this thing. This is the X, and this is the X. This is Y, then this is Y. Sorry. No, yes. Why? These two are, yes, because these two are congruent. These two triangles are congruent. Like that will be a tangent, no? AB will be a tangent and AD will be the tangent ultimately. So that means XX, because ARI and ASI are congruent. These two angles are equal, common side, 90°. And this is Y, right? Now we don't know they are equal or not. If they are equal, then done. Okay, we write then this as a Z and this is a W. We don't know whether CQ is Z or DQ is W, right? We have to prove this for in circle. Now what do we know? We know AB plus DC is same as what?
DC plus AD.
That means that is X plus Y plus W plus Z, right? X plus Y plus W plus Z. AB plus AD, AB plus AD is this, right? Okay, I should write like that. I should like that. BC plus AD is y plus z plus x plus w. And we know this is already from the picture, and given what is given? Given that BC plus AD, BC plus AD is same as AB plus CD. Now BC plus AD is this. That means what? Therefore, x plus y plus z plus w, this is x plus y plus z plus w, is AB plus CD. But what is AB? AB is x plus y. That means therefore, but AB is x plus y. That means what? That means what is we get from this two? CD is z plus w. CD is z plus, right? CD is z plus. So z plus w is CD. So this plus this equal to whole thing, right? But we don't know whether this point is point of contact or not. How do you prove that? How do you prove that this will be z and this will be w? How do you prove that? We already draw the circle which touch AD, AB and BC.
Here tangent, so the dq will be w, which is adjacent.
No, dq may not be tangent. That we have to prove that AC is tangent. DC is tangent. We have to prove that DC is tangent.
You're touching only one point. That's
What?
Q point. The circle, if I draw,
which touch AD, AB and BC. We don't know this circle touch CD or not, right? But we get sum of these two is same as CD plus DQ. Okay. Clear?
Yeah.
Then how to prove that?
if we dot d to I, di joint, di IC. And the point is the point is di and IC. So
What?
we join di and IC.
Okay, we can join DI and IC.
The angular factor.
No, we don't know whether angular etc or not. We don't know.
So then you can say that they are DQ and what I can say, congruent.
These two are congruent?
Similar triangles, I can say.
We don't know these two are congruent or not.
IP are equal.
We have to prove that IQ and IP are equal.
Then it was the CQ and PC is also.
If we can, yes, we can prove that CQ is equal to PC, automatically DQ equal to SD automatically, because some of these are equal to this.
AB equals DC, so that
What?
AB equals to DC.
No.
Sorry, AB plus DC is equals to.
That we already used. AB plus DC equal to BC plus AD. We use from that, using that thing. We ultimately we get this CD equal to this part.
Then CD is also equals to Z plus W.
Yeah.
CD equals to Z plus W. Then DQ plus QC is equal to Z plus W. Yeah.
CQ plus?
DQ plus QC.
Yes, DQ plus C is Z plus W.
We have to find it. By comparing, we can say DQ equals to Z.
No. 6 plus 5 equal to 9 plus 2. We can't compare 6 equal to 9 and.
First of all, the angles are equal. IPC and IQC are equal because they are 90 degrees. First thing you can say.
What?
IQC and IPC.
IQC. This is perpendicular.
This is one. If I go for congruency, that or similarity even. That's one point. IC is the common arm. So there it's
Okay.
also equal to
Okay, I'll put this. Okay. Okay. Now, take this is the R, say. This is R. Now we don't know this is R or not, right? Now, what happened? From Pythagoras theorem, what we get? You have to use the Pythagoras theorem now, right? Now, Pythagoras theorem, IC square is what? Using Pythagoras theorem, what is IC square? IC square is using Pythagoras theorem. So, R square plus Z square, right? And if I use this Pythagoras theorem on the circle IQC, what will get?
then that also equals to R square plus Z square.
No, this may not be R. This IQ square, say this is a H square plus
CQ square.
CQ square, right? So, R square plus Z square is A square plus CQ square. If I use Pythagoras theorem on the triangle ISD, what do you get? ID square is what? R square plus W square, right? And this equal to
H square plus DQ square.
same as A square plus D. Very good. Now, can I find something we can find from this too? You can forget about IC square or ID square. So, we have two different. So, should I write now what we have now? We have this thing R square plus Z square is equal to A square plus CQ square. R square plus W square is equal to thing we have CQ plus DQ is Z plus W, that also we have. So, can I some algebraic manipulation and we can find some CQ plus DQ, or we have to eliminate that H and R both.
Then if you subtract,
Subtract, right? If I subtract this, what happened?
then Z square plus
Yeah, Z square minus W square is equal to CQ square minus DQ square. Now, A square minus D square formula. So, here what we get? Z plus W into Z minus W is equal to what? CQ plus DQ into CQ minus, but CQ plus DQ is same as Z plus W. We know this.
cancel it out.
So, it's cancelled. So, therefore, what we actually get? Z minus W is CQ minus DQ. But what we have? Z plus W what?
CQ plus DQ.
Right. Now, from these two, can we find Z equal to CQ and W equal to DQ?
Yeah.
Now it is easy. A plus B is equal to C plus D. We can't say A equal to C and B equal to D. But say A plus B is equal to C plus D. We can't say that A equal to C and B equal to D. It is not true, right? It is not true. 3 plus 7 is equal to 6 plus 4. So, 3 cannot be equal to 6. But if A plus B is equal to C plus D and A minus B difference and both the difference and the addition is same, then we can conclude that A equal to C and B equal to D. You just add these two, 2A equal to 2C. So, A equal to C, automatically B equal to D. So, we know that Z plus W is C plus CQ plus DQ, but we need Z minus W, and that is why we use the Pythagoras theorem. Clear?
Yes. Now I can draw the square.
So, the converse is slightly tough. If we know that there is a circle inside, we can easily prove that this plus this equal to this plus this, but by tangent property. But if
It's not
if you have the sum is equal, the sum of opposite sides are equal, then finding this whether there is incircle exists or not, that is slightly tough, right. So that means what? That means, and you can easily find that R equal to H then from that. Okay, can you find R equal to H here? No, it's already done because this is now Z. This is, since these are Z, these are congruent, right? Since this is Z, so these are congruent because 90 degree, 90 degree, common RHS. So this is Z, this is W, right? And since Z, this is W, W square plus R square is same as W square plus H square, so R equal to H. Eventually, you can easily find R equal to H from these two equations also, algebraically, without geometry. It's clear? So what actually you get? So if we have something like that, PQR is at the points of the point of contact, 4 tangents, 4 sides, and other figure is inside, right? A, B, C. So what we get? Here you get that AB plus CD, BC plus D, sorry, not the angle, it is the side, BC plus DA, we just in the circular notation, and here the angle ABC plus angle CDA is equal to angle DAB plus angle BCD, right?
Plus 180.
Obviously it is 80. It implies that it is 180. I already told you that if this sum are equal, this is always 180. But we can't say here it is something somewhere bigger sides, but the angles are same, right? So, and if this is true, then the figure is true. This figure is true, then this is asks in online class is that can I draw the both circle, whatever, in what situation we can draw those both circles. So now the figure is combined figure is now. Oh, better I draw the circle. Okay, just a minute. We need the or the inside, no? Inside. Now combine these two figure. yellow circle, inside that blue quadrilateral, right, and inside the white circle, this figure. This is slightly tough to draw, right? You have to slightly adjust. Oh, drawing figure is very tough. After drawing that quadrilateral, drawing circle is very tough. Okay, now it is. Okay, now it is. I can't draw better than that. Okay, so combining these two things. Now this we have to name this point S P Q, this point of context. This point, this point. Now combining these two, what we get? If this figure is true, then both this also true. Opposite sides are equal and opposite angles are equal. Some of the opposite angles are equal. No, sorry, not the opposite sides. Some of the opposite sides for the two pairs are equal. Some of the opposite angles of the two pairs are equal. Okay, so now the question is for which type of quadrilateral this is true. Obviously, that square is true. Confirm. Then what are the others? Is there any other quadrilateral for which this both the property is true? Trapezium, yes, is not of the any trapezium. It is a any type of trapezium. Okay, first the rhombus. In this rhombus, can I draw that one, the outside? Some of the opposites are equal. No, why? Yeah, but can I draw the inside circle? Yes. Inside circle you can draw. Outside? Yes. Why? Why? No. Outside circle means outside circle means the angle, opposite angle in rhombus, opposite, some of the opposite angle may not be equal. In that situation, it is a square, right? Okay, we just first now draw the. We first discuss on the parallelogram only. Okay, only parallelogram first. What about if this ABCD is a parallelogram? Which parallelogram have this property? Then we can say what else rhombus and other thing are there. So in the parallelogram, what happened? What is the result? If both incircle and circumcircle we can draw, then what are the thing? AB plus CD is equal to BC plus AD, and this is already we have this. We know already what we know. We know this is x, say it is x, then it is x, this is y, this is y. That means this 2x is equal to 2y. That means x equal to y. That means the rhombus. But is any rhombus for any rhombus is true? The other, there are one more property, right? So this angle is theta, this angle is phi, then opposite angle must be theta. No, this is phi. What is 180? Opposite angles are equal, you know that. For parallelogram, opposite sides are equal, opposite angles are equal. Now, what is the condition? Theta plus theta is phi plus phi. So theta plus theta, opposite, sum of the opposite angle for both pairs are equal. That means phi equal to theta. So phi equal to theta, that means they are 90 degree. 90 degree, all sides equal, square is the only thing. Square is the only thing for in the class of parallelogram, square is the only parallelogram which have these two properties. In circle and circumcircle both. For other than parallelogram. Trapezium maybe. Maybe? I think so because my kite. The kite was there. Right? Any kite? You know what is kite? This equal to this. So AB is equal to AD and BC equal to CD. For kite, some of the opposite sides are equal, for right. So this is x, this is x, this is y, this is y. So x plus y is equal to x plus y. One condition done. Other condition?
The angles are also
Opposites, some of the opposite angles are also equal 180 degree. Why? We join this, and then these two triangles are congruent. Then what happened?
then
Is this equal? Why?
angle ADC is equal to angle BAB.
This angle is equal to this. So what? This is equal to this.
And angle AD.
So what? This may not be 90 degree.
Yeah.
If it is not 90 degree, then what happened? Then sum of these two angles is not 180 degree. We can't draw the circumcircle. So for trapezium, this angle must be equal to 90 degree. And this is angle 90 degree, then what happened?
It will be a square.
Why?
Because
Is this square? Why? These two may not be equal, right? No.
no, maybe.
Maybe other thing, other kite. Maybe these two are 90 degree, 90 degree. But maybe y not equal to x. We draw a what? Right angle triangle, scalar right angle triangle, right? Draw a scalar right angle triangle. Always we can draw a scalar right angle triangle. Scalar, x and y are different. Copy this or reflect this. Scalar right angle triangle. Now this figure, opposites, sum of the opposite x plus y, sum of the opposite angles are 180 degree. So we have this. We encircle and circle. Special type of kites where these two these two angles are right.
One of the pair is 90 degree.
Yeah. And if this is 90 degree, then it is a square. Actually, square is actually subclass of that, right? No, square is also a kite. Yeah. What is the definition of a kite? The adjacent sides are equal, adjacent sides are equal. So square is also a type of kite. So this is bigger class. This is a bigger class. So among the parallelograms, square is the only thing. In any other, and among the kites, this is a one general thing which have these properties, and square is actually subclass of that. Square is square, right? So we can say this type of figure, this type of quadrilateral have this both the property holds. That means incircle and circumcircle, we can draw incircle, circumcircle both. Now square is one of them actually inside this. Is there any other figure other than kites? Now we don't need we parallelogram class we done, kite class we done. In kite and parallelogram the intersection part is square. And what are the other? Trapezium?
Trapezium
is trapezium? Any type of trapezium? Or maybe isosceles trapezium? What? Is it true for any trapezium? Is it sum is 180 degree? May or may not be. Yeah, we can always take the smaller angle. May or may not be. If okay, if it is isosceles trapezium. Now isosceles trapezium, you know what is the property? By the way, in the trapezium, what is the property? This sum of these two angles is 180 degree. Opposite parallel. That's why opposite sides are parallel. For this reason, this sum of these two angles is 180 degree. And do you know that for isosceles trapezium, these two angles are equal? How do you prove that? How do you prove these two angles are equal? How do you prove these two angles are equal? For isosceles trapezium, these two angles are equal. angle C and angle D are equal, angle A and angle B are equal. Okay, we prove this both way. First assume that angle D and angle C are equal. Okay, given that this is a trapezium, given that AB is parallel to CD and what, and angle D is equal to angle C, that is given to us, and what we have to show, we have to show AD equal to BC, this isosceles trapezium. Can you show? That is very easy, this part is easy, we just extend this and join. Extend both DA and CB, say they meet at say some E. Now we have a triangle EDC, and in this triangle what, this D angle equal to C angle, that means DE is equal to CE. Now since these two are parallel, say this is say x, this is or theta, this is huh? Well, how it will be, but how do you prove that? So this is theta, then this is also theta, this is theta, because they are similar angle of the parallel side, and AD is the transverse, their corresponding angle, so similar angle. Now this two are theta. Now consider the triangle EAB, then EA equal to B, and subtract. If you subtract, what do you get? AD, take the minus. See, right? Easy. What about the converse? What about the converse? It is given that AB is parallel to CD, and it is given that AD is equal to BC. Then how do you prove that these two angles are equal? Slightly tough. And not that too much tough, it is slightly tough than compared to this proof. How do you prove that?
Visualize this understanding. AD equals to BC is given. Then AD equals to BC. You have to prove that the angle is equal. Then the distance between those points are equal, 1 point. The distance between two lines. At any certain point, if I draw at equal angle, they are equal.
We don't know whether these two are equal or not. Okay, now we just erase this thing. We only know these two are equal. Oh no, sorry, these two are equal or not, we don't know. So that means this is theta, say this is phi, this is theta, this is phi, and we know these two are equal.
If you not to equal,
You have to prove that theta equal to phi, right?
You know that if a parallel line is given and if I draw a line between two lines between them, which is at the same angle, to the adjacent to the line.
Then do you continue or just extend this or not? What?
Is that AD equals to A?
You have to prove that AD equal to BC, that is given.
AD equals to A.
AD equal to AE. No, I don't know. That is depends on the figure, right? If it is something small, say there is something like that. If you have this type of trapezium, then it is bigger, obviously bigger. And if you have this type of trapezium, then obviously this is smaller. So that depends on how much the distance is this between two parallel lines. Try to do this.
You have to prove that the angles are equal.
Yes, we have to prove that the opposite, or not the opposite, the
AD equals to BC and AB and CD is parallel. So in that case, the angle that is made by CD to BC and that's all equals to AD and CD because the line is same. So that each change of distance, the angle varies for each case.
No, we need the similarity thing. We need to use the similarity.
Similarity.
Two triangles are similar, right? Which two triangles are similar?
So the angle
AEB and angle
DEC.
right. Now take this, say x, this is y, we have to prove that x equal to y, right? We don't know whether x equal to y. We know these two are z, right? Z and z. If I prove that x is equal to y, then x plus z is same as y plus z. Since these two sides are equal, then we can say these two angles, right?
Convert the BBT into this.
So if I use similarity for these two triangle, what we get?
Angle AEB.
No, angle using angle is similar, but for similar we need the ratios of the sides,
Ratio of the sides.
right? So what is it?
We know that the top triangle and the bottom triangle are equal.
Similar, right? Then x by
z.
or start with the bigger thing. X plus z by x is equal to
y plus z by z.
Y plus z by z is equal to
They not writing y.
y is equal to what? AB by DC, DC by AB. Then this plus this, the whole thing by x is equal to this whole thing by y. Now subtract 1 from the both ratio. What happened? Subtract 1 from the both ratio. 1 from here. What? Z by x.
Is equals to z by y.
Z by y. So
then is the reciprocal of it?
No, it's x equal to y.
X equal to y.
Z cancel.
X equal to y. Oh yeah, then
Oh, x equal to y means it is ED is equal to EC. That means two angles are equal. Clear? You have to use the similarity. So for what? Isosceles trapezium, we have this thing. So again, so draw the isosceles trapezium. No. Now draw any trapezium, and say this have this property. What? What property? That in circle and the circumcircle we can draw in circle and circumcircle. In that situation, what happened? Okay, we first draw the isosceles trapezium. Sum of these two angle is, and these two angle are equal, right? Theta, theta, phi, phi. And we know what? Theta plus phi is 180 degree. That means what? Opposite angles are equal. Sum of the opposite angle is 180. That means we can always draw a circumcircle. Can I draw in circle? To draw in circle, what we need? We need AB plus AB plus what happened? Everything gone? Okay, we can draw this. We draw isosceles trapezium. Theta, theta, phi, 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 phi. Theta plus phi is 180 degree, and these two sides are equal. AD is equal to BC. But we need what? Already one thing we got, and we need what? AB plus DC, okay, is same as, so twice AD. AD equal BC. So is it true for anything, any isolated trapezium or special type of isolated trapezium?
I mean, there is special cases, I guess.
Obviously, if these two are 90-degree, then it is a square, and square is the subclass of that, right? If I take AD equal to BC is equal to AB, and these are 90-degree, then it is square. So square is also inside that. So is this square is the only figure for this? That is the question. Now is the, can I, okay, can I draw any other than square where AB plus DC equal to 2AD?
Yes, just
How?
in assumption, you can say that if AD and BC are 5 centimeters, then AB is 4 and CD is 10. You can draw
May
this.
not be. How do you know? How do you know we can always draw this?
I can try even.
Okay, if it is not isosceles, can I draw this? Can I draw the circumcircle? For isosceles, okay, isosceles opposite, sum of the opposite is 180 degree. For with not isosceles, what happened? It's not isosceles. Then is sum of these two angle is 180 degree? I think no. Why? Clear. Because it is a bigger side and draw a smaller side, same as AD. Draw another side. So this angle is not equal to this, it is smaller. Now cut this. Now this angle equal to this angle. Okay. Now sum of these two is 180 degree. We already proved. Since these two are equal, isosceles right angle, isosceles trapezium, sum of A angle and that angle, E angle is 180 degree, but C angle is less than E angle. So sum of A angle plus C angle cannot be 180. It's 180 if and only if this is isosceles trapezium. So the trapezium, in trapezium, that must be isosceles for draw a circumcircle. For drawing a circumcircle. Now next question, can I draw a incircle for isosceles trapezium? Other than isosceles trapezium, we can't draw a circumcircle, right? It's not concyclic. ABCD is not concyclic because sum of opposite angles is not 180 degree. So sum of two angles are opposite angles are 180 degree if and only if it is isosceles trapezium. Now for isosceles trapezium, we need extra condition here to incircle, for draw the incircle. So is it true, always true, or can I draw other than square, this type of thing? Intuitively we can know. Why? So basic idea is this, okay, we draw say something say this like this. This is not the proof, this is a basic idea, conceptual idea. We draw this isosceles trapezium, right? Draw this isosceles trapezium. Now clearly AB plus DC is bigger, clearly, right? A plus BD is bigger than AD plus BC, clearly. So you can't draw in circle. It's clear that if you try to encircle, it can't touch. If it touch AB and DC, it can't touch, far away. Now we just move this AB just like that.
Near the top.
So in that situation, AB will be smaller. That means AB plus CD will be smaller, slightly smaller and smaller and smaller, and AD plus BC bigger, and in some situation they may be equal. There is some sort of, is called continuity. So one quantity is smaller than other quantity, slightly increase and other is decrease. It may happen that after some time it will be in the top. So one triangle. That time AD plus BC must be bigger than DC, right? Some of two sides. Some of two sides must be bigger than that. So that means start from this figure, end with this figure, right? We start from this figure, this is starting figure, and end figure is this, both are A. B also A. Both are A and B are both same. Now, in the end figure, AD plus AC is bigger than DC. But starting figure, AD plus BC is smaller than, it will be very close say. Now somewhere since it continuously increase, continuously AD plus BC is increasing and continuously AD plus DC is decreasing, somewhere it must be equal. That is sort of analytical concept like continuous function or like that. So do not go with this. So it is intuitively okay, we have this for every, if I take any angle, start with any angle, draw a isosceles trapezium with base angle anything whatever other than 90. If it is 90 then it is square, if it is 90 then this figure must be square, other than 90, less than 90 obviously not obtuse. Okay, you can draw the obtuse, then the other way is just a down then. So take any angle, complete the isosceles trapezium, and then if this is sum of these two sides is bigger than sum of these two sides, just go above. If sum of these two sides is smaller than sum of these two sides, then go downward, and somewhere it must be equal. So we have this type of isosceles trapezium, special type of, not any, we just draw any isosceles trapezium. We can always draw a circumcircle but not the incircle. So the isosceles trapezium with this property, AB plus DC is twice AD. With this property, isosceles trapezium have incircle and circumcircle both. Okay. So I think in online some student asked this. So these are the other situation. And the next question, is there any other? We discuss on the in the class of parallelogram, we discuss in class of trapezium, in class of kite also, but maybe there are several other quadrilateral which is not kite, not trapezium, not parallelogram. What about in that situation? Can I draw something like that? That is a question, big question. That is also answering this question is not that easy, but at least we draw two such classes of quadrilateral which have incircle and circumcircle both.
We have to draw the two circles and then joining the points in that way.
No, we have to find the one condition is very easy. We have to measure this opposite angles are sum is 180 or not, and other is just we have to add these opposite sides. So that always we can check whether it is true or not. The question is, really is there? No, other than this, other than isosceles trapezium of this kind and square. Now, then it is homework to you that you just draw me in the next class, show me one quadrilateral which is not square, not isosceles trapezium, but still the sum of the opposite angles is 180 degree and some of the opposite pairs are equal. You have to draw using scale and protector, everything, compass. Not like that, okay, 1.1 centimeters difference, okay, don't do this. Exactly, okay. So this is very interesting thing. Now, slightly with just for the any polygon, not only for the quadrilateral, is it true for any polygon like pentagon or hexagon? Can I have such a polygon which have incircle and circumcircle both? So forget about the incircle first, we start with the circumcircle. So draw the circle first, and how do you draw a polygon inside this? So take any 5 point or 6 point, right? So 6 point, join this 1, 2, 3, 4, 5, maybe 6 is the hexagon, right? It is the hexagon, cyclic hexagon. But intuitively incircle we can't draw, right? Intuitively, because this is cyclic. But can you say which type of polygon the incircle and circumcircle? Exactly, regular polygon. Like in quadrilateral, what is the regular quadrilateral?
the sides are equal.
And all the angles are also equal. All the sides are, rhombus is a, all sides are equal, but rhombus is not regular. The definition of regular polygon is all the sides are equal, all the angles are equals, both condition. For quadrilateral or for triangle, if all sides are equal, automatically all angles are equal. Equilateral triangle, if all angles are equal, all sides are equal. But for quadrilateral, if all sides are equal, may not be all angles are equal, rhombus. And if all angles are equal, may not be square, all sides are equal, maybe rectangle other than square, right. So regular polygon means all sides are equal, all angles are equal. How to draw a regular polygon? Same idea. How to draw the regular polygon? Draw a circle, then how do you draw the regular polygon? Okay, good, take the center, and if you want to draw say regular heptagon, so say divide the whole 360 degree as seven equal part, right. So equidistance part 1, 2, 3, 4, 5, 6, 7, 8. So it is a regular octagon like that. So this must be equal. Now it is regular octagon, right. Now if we take this equidistant same equal arc, equal length arc, then why it is regular? Since the arc length are equal, the side are also equal. But why these angles are equal also?
Because they are.
If sides are equal, angle may not be equal, like rhombus. Yeah, then join this, join this, join this, join this. Then why these angles are also equal? This all are not equilateral triangle. If it is a hexagon, then it is equilateral triangle. It is a hexagon or a heptagon. 1, 2, 3, 4, 5. It is a octagon. No, it is not equilateral triangle. How it is equilateral triangle? If all are 60 degree, then 60 degree means 6 part. If it is a hexagon, if it is a regular hexagon, there is all triangle equilateral. No, but this must be congruent. Why? Already we by construction these are all equal. Because the all angles are equal, therefore the all arc are equal.
The radius are also equal.
Yes. So this equal to this. That means side SSS. But this two side may not be equal. It's equal if and only the n equal to 6. Only one case. Since all equal, that means what? That means this angle equal to this angle. So this is theta, this is theta. Again, this is theta, this is theta. So all are 2 theta. Right. So this is regular heptagon or octagon, whatever. You have to take 7 or 8, whatever n points, equidistance point, equal arc. So the angle at subtend at center is just 360 degree by n. Right? Then we get the n polygon, regular n polygon. Now, okay, for regular n polygon, this all are equal, right? Okay, how do you prove the other way? Okay, we already regular polygon is given to us. How do you prove this concyclic? How do you prove? Here we already draw the circle and we have the center. Now I gave you that regular hexagon. Why it is concyclic?
Yes.
Why it is concyclic? How do you prove it is concyclic? All 6 points on a circle. You have to find the center. How do you find the center? Where the center lies? Do you know?
Where all the points coincide.
Yeah. Obviously, the center always lies in the perpendicular bisector. So draw the perpendicular bisector of one of them, right? And other, and join this. Very good. Then you obviously join these points, no? This equal to this. By the way, all sides are equal. So this equal to this part, every part are equal. So this is x, this is x, this is x, because two sides are equal, 2x, 2x. Then obviously this 4 are congruent triangle. That means this blue lines are equal, R, R, right. We get this center. Then how do you prove this is actually a center? How do you prove this also the other distance also, say it is A, B, C, D, E, F. How do you prove that these are also R? Now all you have to use the all angles are equal. We use only the all sides are equal. That means what? Say this is theta and this is theta, this is theta, this is theta, but this is complete 2 theta, right? And since all angles are equal, that means this is also 2 theta, that means this is theta and this is also theta, right? Clear? Got it? The 4 triangles are congruent, that means this is theta, this is theta, because they are both radius. I do not know whether radius or not, both are equal. These are congruent, both are equal. Why they are congruent? The two sides, this side is equal to this that side, this is common, so side angle side 90 degree, side angle side. So congruency. Now we have to use the all angles are equal. So now this is theta, so this is theta, this is theta, so this is theta. These two are congruent triangle, so this is also theta. Now this angle is 2 theta now. That means this whole angle is 2 theta. Since this part is theta, that was also theta. Since this is OF is theta, then OFA also theta. Next, what we will do? Again, draw the perpendicular now. Draw the perpendicular from O to CD, O to AF. Right? Now again, compare this triangle with this triangle. Two angle of theta theta 90 degree 90 degree. Angle side. Congruent angle. Then this also R. Similarly, this is congruent R. Then join. Next part is to join this. Again, you can prove these two sides, these two triangles are equal. How? Already. Why congruent? These two angles are equal. This is common side, and this is R. This is R. So RHS. So that means this is theta. So again, this is theta. This is theta. And again, take drop the perpendicular. So drop perpendicular. Next join. So it is not for 6. If you have say 100 many sides, take perpendicular set of 2 sides. Get the point. Actually, is going to be center. 4 triangle. Then join this one more triangle. Then drop the perpendicular. Join perpendicular. Join. Congruent. So is for one time it is angle side, next time it is RHS. Angle side, RHS. Angle side. So any question? No. So that means this is center. So that means we have a center. If it is a regular polygon, we have the center, so we can draw a circumcircle. Now the question for regular polygon, can we draw in circle always? In the next class, I will discuss on that. Okay, I will prove that for a regular polygon, we can always draw in circle also. And obviously, the next question will be for any type of polygon, whether the regular polygon is the only one case. Obviously, for 4, it is not. Other than square, we already get some other thing, right? Some type of kite and some type of that isosceles trapezium. So the question will be for 5, 6, more than 4, whether the regular polygon is the only thing. Okay, regular polygon done. For regular polygon, whatever the n value, for regular polygon in circle and circumcircle always we can draw. But for bigger than 4, the question is slightly tough. So we'll discuss in the next class. For any type of for any n, the regular polygon have in circle and circumcircle both. Okay, that's in the class.